Right. So it's a consequence of having a chiral center present. And you said something about there's some
The
criteria.
carbon atom having, yeah.
So you have 4 different substituents, right? What else?
It's non-symmetrical.
sp3 hybridized, non-symmetrical, good. There's one more thing.
And the mirror images are going to be non-superimposable.
That's good. That's good. You off to a good start. Right. So the mirror images are non-superimposable. What that means is that, let me pull this back up. So you can see my hands. If you have your left hand and right hand, if you show them to each other, that's like they're like looking in the mirror at each other. But when you take the right, try to lay it on top of the left, you see how the fingers don't match? That's what it means to be non-superimposable. So all the other criteria.
Enantiomers.
Say again?
So enantiomers.
Yes. So all the other criteria, they kind of lead to that fourth criteria, which says that the mirror images are, if it has 4 different substituents, if it's sp3 hybridized, and if it's non-symmetrical, then by default, when you draw the image and the mirror image, the two are not going to be superimposable. So let me give you an example. So here's a carbon, right? I'm just going to do a generic. Let's put a CH3 here, H, Br, and then OH, right? So this is a typical tetrahedral carbon. And that's really how chirality is possible. If the atom is based on the geometry of the atom. If it's tetrahedral, then it's a potential for a chiral center. Right, you know the carbon geometry is tetrahedral, right? It's 109.5 bond angle, sp3 hybridized, meaning it has 4 different things around it. And so if this is one image, then the other image, the mirror image, I'm going to draw it like over here. I need more room. Hold up. Let me move this over. Sorry. It's on the recording though, so don't panic. All right, so if this is my carbon, what did I have up here? CH3, H, Br, and then OH. So in the mirror image, if I draw that, I should have had my models. This is what the mirror image would look like. Are y'all following that?
Yeah.
And so when that's the case, these two, the relationship between these two are what we call enantiomers. Right? An enantiomer is just a non-superimposable mirror image. And let me turn my camera off too right quick. Hold up. Oh, never mind. Right, so enantiomers are non-superimposable mirror images, right? They have 4 different substituents. So this carbon right here, this is what we would call a chiral center. Right? In some textbooks, when you read it, you'll see it called a stereo center. Right? Both of those terms are interchangeable. Chiral center, stereogenic center, all interchangeable terms. They all mean the same thing. It's an atom that is a chiral center, or that has chirality. It's got 4 different groups. It's sp3 hybridized. It's non-symmetrical, and the mirror images are non-superimposable. So if I were to try to superimpose this image, let's go ahead and get this out of the way. See if we can have a little bit of 3D action. If I were to try to superimpose the image on the right, onto the image on the left, what would you do? By superimposing, what I mean is that I'm trying to line all the atoms up on top of each other. What would you do?
Could you rotate it?
Rotate it, yes, you could, and that's exactly. So one of the things about chirality that I didn't mention a second ago, but I'll mention it now, is, well, not chirality, but let's say, let me back up. The enantiomers, the relationship between them is that they're non-superimposable mirror images. What we call those as a generic term are stereoisomers, right? We call them, they are stereoisomers. They have the same formula, but they have a different 3D orientation. So anytime we try to superimpose stereoisomers, it's always going to be some type of movement, right? Some type of rotation. You can't detach atoms and move them around, but you can alter the 3D orientation of the molecule. So you're right, we can rotate it. How would you rotate it?
I think it would go counterclockwise.
Okay, so let's think about this. That's good. That's good. I'm glad you're thinking that way. And so you see how this is a tetrahedral? Can everybody see that? How many people we got logged on right now? Let me look. Oh, we got 30 people. All right. I wish I could break this class up into 2 sections and have smaller groups so we can have more engagement. I'm gonna figure that out because I have an idea, but I just didn't want to spring it on y'all right away. But we're gonna figure it out. So can you see the geometry? Anytime you have a tetrahedral like this, right? If you want to try moving it around in space, the easiest thing to do would be to put an axis here, up through there, right? You've been in Kroger before, seen them rotisserie chickens, kind of on a skewer, just rotating away, cooking all day, right? So you can rotate this around this axis. Are you following that? If you don't see it, say something.
Hold on. Wait, your camera.
Oh, wait, you talking about rotating it around the methyl group?
Mm-hmm. So
not the carbon?
Yeah, so imagine there's a skewer going through this carbon right here. You following?
Mm-hmm.
Mm-hmm.
And that methyl group is pointed straight up, right? You remember your geometries from CHEM? So that methyl group, so basically this bond right here between these 2 carbons, that imagine sticking a skewer through that bond, through both of those atoms. Are you following?
Mm-hmm.
Yes.
And then rotating around that axis. What would happen to the OH group if I did that?
It's gonna move.
If I rotate it counterclockwise, according to this arrow right here, right? Let's see what would happen.
Would it be going to the left?
Yeah, would the OH go?
Everything would move to the left. Is that right?
Yeah.
So let's redraw it. The methyl group is going to stay, excuse me. The methyl group is going to stay where it is. Come on now, don't do that. I talk to inanimate objects, by the way, so I'm not crazy. The methyl group is going to stay where it is. And then when we rotate it around, the OH is going to end up over here. Is that right?
Well, are we just rotating the bottom part, not the...
It's kind of like if I need my model, because you could understand it if I had a model and I'm just rotating, yes, like the bottom part, kind of like like if you're turning a knob.
Right.
You understand what I'm saying? That's what we're doing.
Like a carousel.
Yes, that's exactly right. A carousel. You're exactly right. So the three groups here are your horses on the carousel. I like that. I'm gonna steal that.
And Dr. Bissell.
Yes.
I remember in the video, hold on, I wrote it down. It said that, wait, dang it, where I read it? It said, yeah, that the priorities 1, 2, and 3 have to be facing you.
Yeah. We're gonna get to that. That's what we're trying to do to configure. We're gonna do that in a minute.
Okay.
Yeah, but you're right. That's when you put it in what's called a steering wheel.
Right.
Yeah. Hold 1 second. I'm glad you watched it though. I wish I could give you a high five. I'll give you a fist bump through the camera.
Hey, I'll take it.
Yeah. So when we rotate around to the left, the OH is going to end up where that bromine is, isn't it? Something like that. So let's see what happens. So rotate it around. We got the OH over here. What do you think is going to happen to H? Where's H going to end up? Is it going to still be dashed? When I rotate that around like this,
It'll be wedged.
it's going to be wedged. It's going to look just like it's going to look just like this bromine right here, isn't it?
Yep.
Yeah. So let's do that. So let's draw that way. So now this is H, and then the BR will be on a dashed line like that. Are you following that?
Is that always going to be the case?
If it's in a tetrahedral geometry, yes.
Okay, so the dash will become the wedge.
Yeah, if you're depending on how it's oriented now. If it's oriented like we have it drawn here, right? In a tetrahedral, then you can rotate as many times as you want. You can keep rotating those atoms. But what I'm trying to do is I'm trying to show you that you're not going to be able to lay the two images on top of one another and that all the atoms match up, right? And they shouldn't, right? Because we just said that if the mirror image is non-superimposable, then they shouldn't match up. Is that right? So let's look at it. Let me zoom out some so you can see it. What do you think? Can y'all see both images? Now let's say if I took this image down here and tried to lay it on top of this image, because that's what I'm doing. This is just, it's the same, it's still the enantiomer, it's just reoriented.
Okay, but question, when there's a wedge, doesn't that mean that's in the front and then there's a dash that means it's back? Okay.
It does. So let me clarify. I'm glad you asked that question. Anytime you have an atom on a wedged bond or darkened bond, that means it's coming out of the page or coming out of the screen. If it's on a dash, that means it's going back into the screen. And that's just a consequence of carbon being tetrahedral. That's just the geometry. That's how it's going to always be like that. Does that make sense?
Yes.
All right. Can we take the enantiomer, which is down here, and lay it on top of this one right here? What's going to match?
The OH.
The OHs will match, right? But will any, and the methyl group will match, but the H and the BR won't match. Is that right?
Yes, that's right.
So that's why we say it's non-superimposable. You can never get all the atoms to lay on top of one another. If I had, normally when I teach this in class, I'll make a bet. I will bet somebody lunch that they couldn't make them match up. And some sucker, they take the bet every time and lose. I can do it, but it doesn't matter how many times you rotate it in space, you'll never be able to get those atoms to match up if it's a real mirror image. Does that make sense?
Yeah.
All right. So again, let's recap a little bit. So what's the chiral center? It's any atom that has 4 different constituents, that is sp3 hybridized, and that's non-symmetrical. And because of those 3, the last criteria is what? The mirror image is not superimposable. If it meets the first 3, the 4th one is by default. You can't superimpose it if it's sp3 and non-symmetrical and 4 different groups. Are y'all following that?
Yes.
Anybody not following, say something, because this is a pivotal point right here when we start talking about the next type of stereoisomer. And also to recap, these are what we call stereoisomers, right? They have the same molecular formula, but they have a different 3D orientation. That's the difference. That's what a stereoisomer is. Same molecular formula, different 3D orientation. All right, let's move to another, let's see, let me go back. Let's move to another document. All right. So let me show you, can y'all still see my screen?
Yes.
All right, so this compound right here, if you've been in the assignments folder, you can't see the assignments because it's not available. I'll make it available today. So this is atorvastatin, Lipitor. It's a cholesterol drug. All right. Why is this important? It's always important to understand why you want to know something, why you're learning something. So chirality, how many of you are bio majors? Let me see if I can pull this back up. Okay. Got one person responding to that. All right. Okay, good. Good. If you're a biology major, then you know that if you are in the body has receptors, right? In the cells. That's how drugs work. The receptors in the cell have a certain shape, and so drugs have to be synthesized to fit into those receptors. That's why when you take ecstasy, that's why you get depressed after it wears off or after it's eliminated from the body, because ecstasy has the same shape as dopamine. And so what the ecstasy does is it binds to the